The answer on your screen may have begun as rock blasted from the ground years ago. You type 7 words. A paragraph appears. It feels instant, weightless. But the real reason that answer exists is stranger than the software itself. Before it became language, it passed through mines, refineries, chip factories, power stations, cables, and data centers filled with machines that only a few companies can build. Break one key link, and the intelligence on your screen can become slower, more expensive, or impossible to scale. That is why, on December 12, 2025, 7 countries signed a declaration in Washington: Australia, Israel, Japan, Singapore, South Korea, the United Kingdom, and the United States. They called it Pax Silica. It was not a military alliance. It created no central command. It was not legally binding. Yet it tried to connect nearly every physical layer beneath artificial intelligence. That raises a larger question. What happens when the materials, factories, energy, infrastructure, and models behind AI begin forming trusted geopolitical blocks? Start with one chatbot answer. The words come from a model inside a data center. That model depends on accelerator chips doing immense calculations. Those chips depend on memory, packaging, silicon wafers, fabrication plants, chemicals, lasers, and machines so precise that dust can ruin the product. The factory needs electricity, purified water, engineers, suppliers, and transport. The servers need cooling, transformers, networks, and cables under oceans. Then the chain moves backward again. Metals must be mined. Minerals must be refined. Parts must be made. Power must be generated. Every stage must reach the next at the right quality and time. AI may look like software, but AI behaves like an industry, and that industry is growing faster than many systems supporting it. The International Energy Agency reported in 2026 that data centers used about 485 terawatt-hours of electricity in 2025. By 2030, that could reach around 950 terawatt-hours. Electricity use by AI-focused data centers could triple. More AI needs more chips. More chips need more factories. More data centers need more electricity, cooling, water, and land. Demand turns ordinary industrial parts into strategic bottlenecks. A delayed transformer can hold up a data center. A memory shortage can limit AI servers. A restriction on chip-making equipment can slow a national industry. The strange part is that no country controls the whole chain. Different economies dominate different links: design, fabrication, memory, equipment, and minerals. Specialization made technology cheaper and more advanced. It also created dependence. A 2026 United States Government Accountability Office report noted that about 3/4 of chips were manufactured and packaged in Asia as of 2022. Concentration is efficient when everything works. When something breaks, efficiency becomes fragility. The chip shortage that began in 2020 showed the effect. Factories had workers and materials but could not finish products because tiny electronic parts were missing. A United States Commerce Department analysis estimated that the shortage contributed to 7 million fewer cars being produced in 2021. That was not an AI crisis. It was a preview of what one choke point can do. Now add national security. The same systems used for research and language models can also support surveillance, cyber operations, autonomous machines, intelligence work, and advanced weapons. The cheapest supplier may no longer feel like the safest. Governments begin asking not only, can this company deliver, but can this country still deliver during a conflict, sanction, disaster, or political dispute? That fear is the cause. Pax Silica is one possible effect. The declaration covers minerals, energy, manufacturing, semiconductors, computing, networks, data centers, foundation models, software, and investment security. The name sounds as if it is about silicon. The key word is trust. The governments want critical parts of the chain to move through, dependable partners. They want investment to strengthen preferred suppliers and reduce exposure to disruption. Since the first signing, the network has expanded. India, Sweden, Finland, Norway, and the Netherlands joined during 2026. On June 25, The European Commission signed on behalf of the European Union. The official declaration does not name China. That distinction matters. Pax Silica is not officially written as an anti-China pact, but the rivalry is difficult to ignore because several critical stages are heavily concentrated in China. The International Energy Agency found that China accounted for about 60% of mined magnet rare earths in 2024, 91% of refined output, and 94% of sintered permanent magnet production. Rare earths are not silicon chips, but they are vital to motors, power systems, industrial equipment, defense technology, and infrastructure around advanced computing. So dependence creates fear. Fear creates cooperation. Cooperation creates protected networks, and protected networks can produce two different futures. The first is resilience. Countries combine strengths instead of trying to build everything alone. New mines and refineries reduce dependence on one processor. New chip factories spread production. Added energy systems support data centers. A disruption in one country no longer stops the whole chain. Investment can create jobs, skills, and industrial capacity. Companies may gain more stable suppliers and consumers may face fewer shortages. But the same cause can create a second effect. Duplication is expensive. A semiconductor factory can cost tens of billions of dollars and take years to build. Mines face long approvals. Grids often expand more slowly than data centers. Governments may subsidize plants that cannot compete without support. Security can also reduce efficiency. A part may be bought from a trusted partner even when another supplier is cheaper. Those costs can move into taxes, electronics prices, cloud services, or AI subscriptions. Then comes the physical cost. More chips require more materials. More data centers require more electricity and cooling. More infrastructure requires more land, water, and construction. The benefits and burdens may not fall on the same people. One country may provide minerals while another captures the value of chip design. A community may provide land and water while a distant company owns the data center. A secure supply chain for one group can feel like extraction to another. Then trust creates a boundary. Countries inside the network may receive more investment and access to advanced computing. Countries outside may face tighter export controls, fewer suppliers, or pressure to choose a side. That does not mean Pax Silica has already divided the AI world. It remains a non-binding framework, and its effects depend on later policies and investment. But alliances can shape expectations before they shape laws. Once companies believe subsidies, contracts, or export permits will favor trusted partners, money begins moving in that direction. Rival countries can respond by funding local alternatives, limiting exports, building different standards, or creating their own partnerships. One protected network produces another. Resilience inside each block may increase. Connection between the blocks may weaken. That is the uncomfortable chain reaction. Dependence creates fear. Fear creates cooperation. Cooperation creates protected networks. Protected networks create exclusion. Exclusion creates competition, and competition can divide systems once built to work globally. Past eras organized power around sea routes, coal, steel, oil, nuclear material, and finance. The AI era may be organized around a new combination. Minerals, chips, energy, data, computing power. Pax Silica matters because it tries to connect all five through trust, not ownership, not complete control, trust. And trust is never shared evenly. Return to the answer on your screen. It still appears in seconds. Nothing in the text tells you where the minerals were refined, who made the processors, what powered the data center, which cables carried the request, or which government could interrupt the chain. The intelligence looks invisible. The system behind it is not. It is underground, inside factories, across electrical grids, beneath oceans, and between governments deciding who counts as dependable. The countries connecting those pieces today may shape who receives the most powerful technology tomorrow. And if intelligence becomes the world's most valuable resource, will countries still share the machines behind it, or only with the nations they trust?